Okay, let's look at some substitution techniques for integration. With these problems, you're going to want to try to find the terms that are collected in parentheses or under a radical. They're usually grouped somehow. But if you go with the bulkiest part, for example, in this one, 4 plus 7x, it's wrapped up in parentheses to the fourth power. If we let that be substituted by a single letter and use very common, and we take the derivative of both sides, the derivative of 4 is 0, the derivative of 7x is 7, and because it has a variable x, we're going to put dx. The idea is between the substitution and the derivative line, when you go back to the original problem, you want your derivative line to make up the non-grouped part of your integral, for example, this 7 dx. We can replace that with du, so our problem becomes u to the fourth, all that's replaced with a u, and then the part underlined 7 dx, we can replace that with du. Now using the integration technique, we add 1 to the power, divide by the result, and add a constant of integration. And like that cliche, you always dance with the one who brought you, change your u back into terms of x, and that gives us 4 plus 7x, all raised to the fifth, over 5, and then don't forget the constant of integration. On our next slide, we have something very similar. If you'll notice, 3x cubed minus 2 is grouped in parentheses. That's always a good place to start. Now, it's not money in the bank, that's where you start, but that's where I always go. And I'll let u be those two terms in the parentheses. Take the derivative of both sides. Dx. Now we go back to the original problem, and the grouped part was the parentheses to the fourth power. The leftover part was x squared dx. From our line that we just have, du equals 9x squared dx, if we divide both sides by 9, then that'll give us something to match up with the original problem, x squared dx. Okay, going back to the original problem, x squared and dx, sorry about the screen shake, we can replace that with 1/9 du. The parenthetical part we can replace with u to the fourth. That's where we made our original substitution. That constant 1/9, we can bring it out. And then now, add 1 to your exponent, divide by the result, plus your constant of integration, and then, like on the last slide, put the original terms back in for u. I'm going to go ahead and call that 1 over 45 just to clean it up. And then we can put that original group of terms back in, plus c. On this third example, we don't have parentheses that lock us in on what we would attempt as our first substitution, but we do have a radical in the denominator. That's where I'm going to start. If it doesn't lead anywhere, you can always erase. But let's start there. I'm going to let u be 3 minus x squared. Take the derivative. That little negative in there is tricky. You got to watch it. Glance over at the original problem. The substitute was in the denominator under the radical. The rest of that integral was x dx. We're pretty close to it in our du line, but let's divide both sides by -2. And that'll put us where we need to be. Looking at the original problem, across the top you have x dx. Let's replace that with -1/2 du. And then our denominator, it looks pretty strange written that way, but our denominator is square root of u, but square roots can also be written with fraction exponents. I'm going to go ahead and call that square root a power of 1/2. Those are two different ways to write the same thing. By properties of exponents, u to the 1/2, if we move it to the numerator, it'll become u to the -1/2. And that gets it a little bit more manageable for us. And there's that little exponent property. Okay, I'm just going to block that off. Okay, let's go back to the problem. We're in midstream. Let's pull the -1/2 out. Add 1 to the power. -1/2 plus 1 is +1/2. Dividing by 1/2 is the same as multiplying by 2. Plus our constant of integration. This 2 and that 2 will cancel, leaving us with negative u to the 1/2, which I'm going to rewrite as a radical, replacing u with 3 minus x squared, and then our constant of integration. Be careful to stop that radical right there. Don't go any farther. The plus c just stands alone. And finally, one other example involving trig with a multiple angle. If this were just cosine of x, its antiderivative is sine x, and it'd be a fairly straightforward integral. This one has an angle of 4x, which we know the derivative of 4x is 4, and the outside of this problem doesn't have just a 4 to help balance it out. So instead of having a group of terms in parentheses or underneath a radical, we can just start with that angle and see how it leads us. Usually that's a good starting point with trig, is looking at the angles if there's not a clean antiderivative. Take the derivative. This problem, we have after the substitution is cosine of u, and the only thing that remains is dx. So back up in that derivative line, let's divide both sides by 4. And now we've got to substitute for dx. 1/4 du. Move your constant out. The antiderivative for cosine is sine. And then we put the original angle back in. So we're going to have 1/4 sine of 4x plus c. I hope this video is helpful, and there will be others in the future.